So it's been about a week since we talked about anything of substance. And here we ended with this driving home example where, according to Monte Carlo, you would be waiting until you arrived home to analyze the entirety of your drive home and say what was the difference between the anticipated predicted time for the drive at that stage versus the reality of what actually happened. Whereas with temporal difference, what we're doing is we're not waiting until the end. We're at each interval looking back and saying, how did this one leg change our expectations? So I like this graph where we look at the actual outcome. And if this is Monte Carlo, then we're going to be pulling every estimate of each step of this journey home to the actual outcome. So the weight here, the gravity is on the actual outcome, and every prediction is going to move toward the actual outcome. Whereas in temporal difference, we're going to be using the next step's estimate to increase or decrease the current, the prior step's estimate. So we're not waiting to get home to update. As we reach the car, we realize that since it's raining and we can see that it's raining now, we change the estimate for how long it's going to get home by 10 whole minutes because it's raining. And I guess this isn't Washington where people know how to drive in the rain. This is, imagine somewhere else in the country where rain is the worst thing that's ever happened to them. And so they don't know how to drive in it. We've all been to those, well, some of us have been to those locations. I've lived in those locations. Those people are wild. Sorry to those people who are watching this video. Learn to drive in the rain. As we reach the next step of this process, we get to exiting the highway, and that turned out to be much faster than we thought, given that it is Friday and raining. So we now are able to update our estimate of just the highway stretch to now be a little bit less than we otherwise had thought, because we now have one additional example of a clean freeway driving experience. We can add that to our average. We're not penalizing based on the truck that we got stuck behind on that secondary road. And that's the main difference in Monte Carlo versus temporal difference, is Monte Carlo is going to fail to attribute kind of a cause and effect, whereas temporal difference will try to account for that cause and effect. If we get stuck here because on our secondary road we were behind a truck, we shouldn't change the entirety of the estimate for everything because we got stuck behind a truck. We're going to just attribute that to the secondary road portion. And that's not necessarily a good thing or a bad thing. If some days we get stuck behind secondary roads and we should increase everything because there's a chance that we're all going to get stuck behind a truck on the secondary road on a daily basis, then maybe it makes more sense to use the Monte Carlo view of the world where we're going to move everything to the result of when we got home. For temporal difference, on the other hand, if that is true, then we should only account for the average time on a secondary road and not punish other aspects of this journey. We keep individual estimates for each of the different pieces of our journey. So I think this is the last couple of slides we focused on. We were going to end with that random walk example we were going to go over. But we talked about the advantages of temporal difference. The online incremental learning is a huge benefit for this because Monte Carlo does online learning, but it doesn't do online incremental learning. We have to wait for an episode to finish. So if your episodes are very long and your discount rate is high, it's going to take a very large sample size in order to get any value out of the first few steps of an episode. Imagine games of chess that last 50 plus moves. And if that's the case, then how many episodes do we need in order to backtrack the result of a win or a loss to the first few moves that we take? It's going to take a ton of samples in order to be able to answer anything about that. Whereas with temporal difference, we're immediately starting to backtrack the values of states. They're kind of propagating back through the games that we play, and eventually those updates are more meaningful. All right, let's get back to this random walk example. Do you remember this random walk example? So we start in vertex C, and the goal is to reach either left or right, these gray boxes. And we're gonna start with randomly moving either left or right half the time. And the true state values here of A, B, C, D, and E are just 1/6, 2/6, 3/6, 4/6, and 5/6. We can see how that is done, but we can get reasonable values for this, and it also tends to show us very nicely the difference between Monte Carlo and temporal difference. Because if the estimates are all initialized to 0.5, and we move left or right with equal probability, we see that we have to wait for an entire episode to terminate before we make a single update, because the estimate of every node is 0.5, and there's no penalty here to making any moves. So an episode of length 3 is the same as an episode of length 6,000 from the perspective of there's no step cost anywhere in this problem definition. So eventually, this process will terminate either in the rightmost gray box or in the leftmost gray box. If we were going to terminate in the rightmost gray box, what would the updates look like? Which nodes change in value and by how much? There is a hidden learning rate to this that we don't see. But a learning rate will tell us how much to value the last piece of data that we have. But the only thing that gets updated is the value of E. Because when we are in E and move right, we get 1. So if our learning rate, we are assuming the value of E right now is 0.5. If we move right from E and get 1, then we can backtrack to E and say, well, when we did this, we now can see that 1 minus 0.5, we netted 0.5 over the expected value of E. And maybe we have a learning rate of 0.1. So if we do that, we're going to take 10% of that difference and add it to this node. So this becomes 0.55 instead of 0.5. This is so we don't overreact to a single example through this. But what happens the next time we start another episode at C and we move right and then right? When we move right, now we're going to see the difference between D's expected value and E's expected value is a value. And if we update that by 10%, then this will back propagate to D, even though the episode isn't finished yet. Monte Carlo would say, wait, we haven't finished the episode. We haven't reached one of the termination points. We can't possibly know that. And temporal difference is updating based on the current value of the node. When we make that move, we immediately backtrack it to the node we came from before we finish. And now from here, we will find that if we move back to D, rather than going down significantly, we'll go down a little bit less significantly because D's value has increased since the last time we were there. And we'll find that as we just continue to explore this space, we get to make updates more frequently than Monte Carlo does. If we ended up going from C to D to E to D to C to B to A to B to C to D to E, etc., and had a 6,000 length run, Monte Carlo would wait for that termination to backtrack all the way through the states. Whereas temporal difference, every single time we're visiting a new node, is getting closer and closer to those actual expected values, given more experience. This is why we say that temporal difference converges faster in practice, because when you do visit the same nodes multiple times, you can still make those updates multiple times, and that will still eventually converge to the real values. So it works extremely nicely in practice. But it is not strictly better. These are two options and they work very differently. So we'll see just how this works in practice. So this is what happens when we use a learning rate and we set the actual, so this is with 1 and 10 and 100 episodes run. And we'll see that initially we have next to nothing. We know next to nothing. Each of these states is valued at 0.5 with the exception of A, because when we moved the way this first episode terminated, we went to the leftmost gray box, We only did a single update to this that dragged the 1 down a little bit, the A down. And as we got 10 episodes in, we found that it's starting to become more apparent that D and E are more valuable than A and B. And we see that with even just 100 episodes, we are reasonably close to the true values that we learned just from experience. And we did not know or calculate those true values. We just simulated and used temporal difference to update values in real time. Questions on this graph? So it only took 100 episodes. That's surprisingly efficient for a learning algorithm like this. Granted, the problem was very simple. Most problems are more complicated than this. So it takes a lot more episodes to terminate on average. Let's take a look at root mean squared error. That's what RMS error stands for. Root mean squared error just says we're going to take the error, we're going to square it. That way it doesn't matter if we're on one side or the other side of the true value, because on one side you'd have a positive error, on one side you'd have a negative error. We square it so that the error is positive no matter what. And we see how fast Monte Carlo learns, and we can see with these different dotted or edges, here is the different values of potential learning rates. Alpha equals 0.01 says that whenever there's a difference between the expected reward and the reward that we see when we enter when we finish, we're going to update by 1%. When we see something that differs from what we expect, we take 1% of that weight, and we add it or subtract it from the overall values of those states. And we see that learning rates, something like 0.01, learns very slowly. It eventually gets there, but it has a slower learning out of the gate. The root mean squared error is higher, which is worse. It's better to be closer to 0 than it is closer to 0.25 for error. We learn a lot faster with 0.02 and even faster with 0.04. But the actual values kind of converge down here. I think this is pretty much noise at this point, depending on the values where they are down here. They should eventually converge to the same values. But we see that temporal difference does not take anywhere near as many episodes, even with lower learning rates. But we'll see that a lower learning rate converges and a higher learning rate at this point starts to overreact. If we're weighting every episode or every step that we take as 10% or 15% of our entire knowledge, we have 100 episodes, but on the 100th episode, we're going to take the value of the 100th episode as 15% of the overall weight of the information that we have. That's what leads to higher issues here when you choose higher learning rates. So we start to bias the results that we're seeing a bit too much. So typical good choices for learning rates are about 0.05 to 0.1, somewhere in there, that allow you to converge reasonably quickly. The higher the learning rate, the faster the convergence. And you kind of see that as 0.15 learns the fastest. It doesn't take as many episodes in order to start approximating the end result nicely, but then it tails off very quickly and doesn't improve from there. So you can also use a faster learning rate and use a temperature parameter to cool that learning rate over time. Start out with something high to learn it quickly. And then once you start to have that base information, don't learn as much from your new deviated data, and that can learn it quickly and converge to the best values. Questions on this?
So something I'm noticing is it's slowly increasing in its error for the so
it's like right here. This
yeah,
is slight.
So it's like a slight slow increase in error.
Yeah.
I mean, eventually I assume it's going to flatten out.
Yeah,
but I just think it's just interesting that because the learning rate is so large that it's slowly getting worse and it's never actually going to fix itself. It's just getting worse.
It's going to stay relatively flat at this point. But yeah, it can get worse because we're in the extreme case. It's like saying if you have a learning rate of 1 and you win the lottery, you think the expected value of the lottery is the winnings of the lottery because you've overreacted to the exact last thing that happened. And even if you give 15% weight to that, if the expected value anywhere near 15% of the jackpot, it would take you a reasonably long time, a long string of losses to learn the expected value is actually low at that point, because you'd have exponential decay, 0.85 for each loss that it would take you to approach zero, and that will happen. But you see that you get massive spikes in error whenever you win because you're drastically overreacting to that win. And then you have to learn via evidence again that it wasn't actually that likely. But that is a good point. Yeah.
You say the cooling off technique would be to use the 1.5 like the first 25 episodes and then switch it to a lower.
Yeah, you'd get down here very quickly for the first 25 episodes, but then you would start to use this. If you're teleporting, you've gained the same amount of knowledge in 25 episodes that our slower learner at 0.05 took 50 episodes to learn. So if you dropped off the 0.15 here to 0.05 at that point, then you could learn this level of accuracy with 25 fewer episodes. But you don't usually want to flip a switch and go from one learning rate to another. You want to cool and say, on the first episode, I'm going to learn at 0.15, then 0.145. Then you slowly decay that exponentially. And that tends to work really well. Any other questions? So what happens if we don't have enough data? That's a big problem frequently. So if it's expensive to gather new data, this could be something like it's survey results and you have to pay people to survey them, or bring people in for a study and have them use very expensive equipment. And that expensive equipment has a chance of breaking as they're using that expensive equipment. Then there's a real cost to acquiring more data. Maybe you're doing a survey on people with a very rare condition, and you need to recruit people with a very rare condition, and there just aren't very many people from which to draw data. Or in order to get data, you need to run on a very expensive server that has a significant cost associated with that server's running. So what happens if we just use a very small amount of data that we have? And what happens if we just try to learn on a small amount of data? What can we expect? Where can that go wrong? So batch updating says that we're going to run a bunch on episode 1. We're just going to run that experience over and over and over again through just our calculation. We're not gathering that data. We just gathered an episode, and now we're going to rerun that episode in our calculation. Doesn't have any cost of acquiring that data. We have the data, just how much can we learn from that? Then we'll introduce episode 2. Once we've learned everything we can from episode 1, we're going to introduce episode 2 and switch back and forth between running episode 1, running episode 2, episode 1, episode 2, episode 1, episode 2. Then we add in episode 3 and run 1, 2, 3, 1, 2, 3, 1, 2, 3 until that converges. So let's give you an example of this to kind of illustrate what this would look like or how this can go wrong. So we're going to play a game. You don't know anything about this system. You're going to play the role of a reinforcement learning algorithm. And what we see is this tells us the associated states. So we observe 8 episodes. And the state is either A or B, and the immediate reward is either 0 or 1. So we see reward, we start out in state A, we see a reward of 0. Via some move that we made, we ended up in state B, saw a reward of 0. And that reward, that B, terminated the episode. The next one, we start with B and have a reward of 1, and that is immediately terminating the episode. And onwards. So it's pretty easy to see what the value of B is. There were 8 total episodes, and when we ran into B, we found that the value of B was 0 twice and 1 6 times. 6 out of 8 would have been our average reward from visiting from visiting B. What is the value of visiting A? The issue here is we have absolutely almost no experience with A. So what could we do to get a good estimate based on this very limited data, what should we do with regards to coming up with a good approximation of the value of A? Suggestion?
If I was looking at a weighted system of knowledge that we only visited A once, so that result doesn't weight as impactfully as the 6 out of 8 times we visited B.
Something that is weighted lowly based just on the fact that we don't have much of a sample size? Sure. There is technically something better we can do. Yeah,
Is there something that you're trying to like link A and B together to some sort of correlation?
kind of, yeah.
Okay.
The question is, what is this underlying system? How likely is it that this system, if I were to have you draw out the graph that is this system, what would you draw? Yeah,
Since the only bit of data that I have is that A and B are the same the one time that they're measured, I'm either going to assume that A is always going to be the value that it is, or that A and B are going to be similar, because that's the only frame of reference for information that I have.
okay. Interesting. So in our sample size of 1, A and B have the same value, and we're going to hope that that generalizes to more than that. It's a good guess.
It's pretty bad, but like.
No, it's a good
there's no
guess. So, is there another way to view this? Yeah,
Yeah, I'm thinking about like a state machine in the sense that they're either A or B could be a start state,
mm-hmm.
and there's a transition from A to B.
So what would we do from there if we wanted to figure out the value of A? If A always leads to B, which it seems like more likely is the case. If A leads to B and we sample B, it is possible, we see that right here, that B can derive a 0.
In my instinct, would be that. Make me,
The value of A is the value of B.
if there's a transition.
Yeah. That's the smart way.
Yeah.
It allows us to fake a larger sample size for this in ways that we don't actually know if that is the case, but we can in a larger sample size game if we make the assumption that A and B are linked. When we start in A, we go to B and then sample from B. And that gives us a sample size of 8 for A instead of a sample size of 1 for A. If that is the case, it'll be a better approximation of the value of A than any other way that this system could be set up. But Monte Carlo is going to have a really hard time doing this. So we look at state A had 0 return in 1 episode, so its value is 0. On the other hand, if we use batch temporal difference, then we see that A derives B or goes to B 100% of the time, in which case what we really have when we sample from A is we are just sampling from B. So we should take all of the experience that we have from sampling B and attribute all of that to A as well. So batch temporal difference will use just these 8 episodes, train on them over and over and over and over again, introducing more, and eventually we derive something that looks like this system. That says that A always goes to B, and B goes to 1 75% of the time, and 0 25% of the time. And it would make sense, right? We have a single episode with starting with A. Does it surprise anyone that a 25% likely event occurred? I flip 2 coins and it comes up heads and heads. Who's grabbing their pitchforks? It's likely enough that it doesn't surprise people. So it would be better to attribute A to this system and get a better sample for it. Is that what the underlying system looks like? Who knows? But with limited information, we can still make that decision, and this is what this converges to. Whereas if you use batch Monte Carlo, this is what you converge to. And that should be A to 0, not A to 1. Questions on the concept of batch learning from small sample? it's easy to see just from how not confident people were in their responses to what's going on in state A, that the small sample is a real problem. But if you don't have any way around it, you make the best with that data that you can. And you can make a conclusion based on a sample size of 8 rather than a sample size of 1, if that is true underneath the hood. And we'll see that, again, looking at root mean squared error, that batch temporal difference does tend to outperform batch Monte Carlo. So if you're ever doing batch learning like this, batch temporal difference is better than batch Monte Carlo on small samples. All right, it is time to introduce the 2 main temporal difference algorithms. These are probably the most used algorithms in reinforcement learning. Obviously, there are bells and whistles to them, but these are the 2 that are most frequently used. First is called SARSA, and we have talked a little bit about on policy versus off policy. We're going to see that come back again in temporal difference. Anyone want to summarize that concept of on policy versus off policy? It's been a little bit since we talked about it.
I could have a mix up, but on policy is when like the exploration is built into the policy. And then off policy is when you have 2 separate policies, one that handles exploration, one that handles like expectation.
Yeah, so the question is, how many policies do we have? You did not get them backwards. On policy, it has 1 policy, exploration is built into the policy. Off policy, we have 2 different policies based on that importance sampling ratio, based on how likely was a particular trajectory that we could simulate, based on the 2 different, one that is optimizing the process and one is using an exploration-based process. So we have 1 policy that tells us what to do and another policy that analyzes what we would have done if we were acting intelligently. Again, I like to think of it as 2 voices in your head, one the inner teenager and one the grown adult. The teenager is going to tell you how to act, and the grown adult will deal with the consequences and try to learn how to optimally behave, even though you're behaving like a teenager. So SARSA just says we're learning action values again, rather than actual state values. We're learning action values. How good is it to be in a state and pick a particular action? TD0 just says we're only looking back to the prior state. TD1 would be looking back 2 states. TD3 would be looking back more than that. And if we took that to an extreme, we would end up with Monte Carlo, looking back over the entirety of the episode. So here's our update equation. We're going to say that the new value of a state action pair is the old value of a state action pair plus our learning rate alpha times this. We're going to call it a temporal difference error. This is the reward that we get at time t+1 for having done that action, plus a discounted, this is going to be the discount rate that we use to determine how much better is it to receive that reward now than 1 step in the future. So we're discounting the existing state action value for the state at time t+1 and the action at time t+1. We're going to subtract from that the value of state time t and action at time t. So this gives us the way that I was doing this before when analyzing the walking example, where when we had a state that we saw at 0.5 and we moved right and we saw a state with a value of 1. This is exactly where we fill that in. This is just going to say the reward for this was 0. There was no movement penalty for that. If there were a step penalty every time we make a move, that's what that would represent. We have our discount factor, then this is the value of where we came from. This is our 1. This is our 0.5. Now I'm thinking of this in terms of states again, and these are done in terms of state action pairs, but that's basically all of this math boils down to just a couple of numbers and what they mean. This is the value of where you ended up, the value of where you came from, multiply this whole thing by a learning rate, that is how fast you want to learn from new experience, and then use that to add to the old value that you're updating. So it's nowhere near as scary as it looks. It's just a few values, and the more you think about it, the more it makes sense. You're pulling the current value in a positive or negative direction based on the example that you just saw. Where did you end up? Where did you begin? What is the difference in those values? If it's positive, you improve the state of things. If it's negative, the value decreased. And so the value should increase or decrease based on the experience that you just had. Okay, so we're changing the policy greedily, and we can guarantee convergence if every state action pair is visited an infinite number of times over the course of an infinite number of episodes. So that means that exploration has to be built into the policy such that we find ourselves in every possible state, taking every possible action in that state for every state. And we'll find that the policy converges to a greedy policy, which makes sense. Pseudocode for SARSA, fairly straightforward. We take in each episode, we're going to initialize our starting state to be whatever the starting state is by the starting state selection policy. Then we choose an action from that state using our policy. Our policy may be an epsilon greedy policy, but we know that because it is on policy, exploration is built into that policy. So if we used epsilon greedy, that tells us there is at least an epsilon chance we're exploiting with probability epsilon, exploring with probability 1 minus epsilon. And that allows us to make sure that we're selecting every action occasionally from the state. So we choose an action based on the policy. Then for every step of the episode, we are going to take the action that's been prescribed, observe the return that we get from that action, the new state that we find ourselves in. Then we make another selection, choose the action from that state according to the policy. Once we've chosen the action, we now have managed to go from the initial state action to a new state action. So we can look at how good is it to be here? How good was it to be here? Let's make an update to where we came from based on what we observed. Then we replace the new state, the old state with the new state, the old action with the new action, and loop back around and pick the next. Pick the next action. Update, loop around, pick the next action, loop around. You just continue this process until the episode terminates. But note that the update here is in this loop, whereas this update was after the loop in Monte Carlo. We had to wait for the episode to terminate and then step back through the episode and apply updates. In temporal difference, that update is embedded within the loop because we're doing it every step of each episode. We're out of time already. We'll come back to this and I'll give you some examples of SARSA running, as well as we'll look at Q-learning, the off-policy temporal difference algorithm that is very similar to SARSA, and we'll start to compare them and see what happens. But we'll probably do that next week because I want to, as I mentioned at the start of class, start in on review tomorrow. So anticipate that. Come prepared with any questions that you have for me for Friday's exam, and we'll talk about that until there are no more questions. Reviews are up. Yeah, great. Reviews are up. Take a look for the reviews that you've been assigned and reach out to either Stephen or me if you were assigned something that doesn't make sense, like your own game. That shouldn't be possible. Come on. Thank you so much for